quickly, I hope, the conduction version of the Atlanta airport. So we've got a rectangular, forget about Atlanta airport and people. It's more like a rectangular plane on which rain falls uniformly. So this plane has 2 dimensions. It's horizontal, and the rain that falls is actually heat that's being generated uniformly per unit volume. So heat generation per unit volume in heat transfer nomenclature is Q triple prime. 1 prime for each of the 3, that meaning you have heat flux is double prime, heat transfer rate per unit length is Q prime. All right, so the boundary is insulated except at one point through which the collected heat current is extracted. So this is the Q. This slab has a 3rd dimension. Let's call it, what do I call it? W again. And the temperature inside the rectangle has to be higher than the temperature at the exit. So if the temperature here is T0, and if the conductivity of this rectangle is K0, where will be the highest temperature? Where? Think of it as water flowing down the pavement, if this is the sink, for the water to flow, it must be flowing this way in the vertical direction and this way horizontally. And these 2 arrows emanate originally from these 2 corners. So the farthest corners, just like the farthest traveler in Atlanta airport that had to spend the most time, the farthest corners are the 2 places with so-called the hot spots, maximum temperature. So what comes next, meaning I decided to do this analysis in an order of magnitude sense. Which is known as scale analysis. Here the word scale means size, as in magnitude. So the object is to, once again, to try to make the coldest hotspot by varying the shape and other features of this particular flow system. So the object of the game is the overall temperature difference, which is Tmax minus T0 when Q is fixed. Q is known. What is Q? Well, Q is this volumetric heating rate times the volume of this slab. It is what? HL and then W. Right away, you know that, meaning you're smelling the existence of excitement here. The shape of the slab is one of the unknowns. Remember? Meaning you should know these things already. But there is more to the so-called design. And the additional feature comes from asking yourselves how to facilitate the flow out of this rectangle. When you do that, there's always one answer. You do that by reaching in your pocket and paying for it. In this case, you buy a little bit of very highly conductive materials, such as copper, but even more expensive gold, and you put it here. This blade has a much higher conductivity called, I call it in the book, K sub P, from the conductivity of the path that collects the heat current. So K sub P is much greater than K0. The blade has a size that's determined by the thickness of the blade, and the size of the material is thickness of the blade, L, and then W. That's the expensive material, divided by the total volume, which is H, L, W. This ratio, because it is expensive, is a lot smaller than 1. And I called it phi. In other words, D over L is the volumetric fraction occupied by highly conductive material. Now, I still, because you're so quiet, I don't know whether you like a joke. Various teachers, I'm not going to name them, talk about simple things, meaning materials that are made of one kind of substance, say iron, or two materials. They call them bimaterials or alloy or something, a mixture of those two. No, that is not what you have here. Here, yes, you have two materials, but they are not mixed. They are configured one through the other. So yes, you have a more complicated construct. You have a composite, but it is a composite with architecture, and that is new. And the architecture is the baby, not to be thrown away with the bathwater. It is the baby. So how do you shape this thing given what you paid for its configuration with contrast? Well, I already erased the technique. You look at the overall measure, which is the across divided by the through. And this delta T has two parts. One is a temperature difference that is oriented in a vertical direction. You can think of it as this temperature difference, delta T y. And then another one is the temperature difference along the, meaning horizontally, delta T x. If on this rectangle you imagine a river in the valley, and you have hills on both sides of the valley, well, the slope of the hill is your delta T y divided by capital H, or half of capital H. And the slope of the river is a delta Tx, meaning the slope of the river bed, delta Tx divided by the path of what flows down that river, which is L. All right? So we have delta Ty and delta Tx. I already told you the order of magnitude estimates of these delta T's. They come from again, Fourier. Remember, Fourier is, I'll just write it for, never mind, Fourier means Q equals K, and then cross-sectional area, and then delta T over path. In the case of delta Ty, the total heat current is all the heat generated. I already wrote it somewhere, didn't I? I wrote it here. Q triple prime HLW. And then that has to be, it's collected over the black portions of the blackboard. All that has to go vertically over a distance h over 2, which is over h, driven by a temperature difference called delta Ty. So it is K. By the way, the cross-sectional area pierced by this vertical flow is L1 times W, not L1, LW, and then delta T Y over H. So yes, coming down is this heat current, cross-sectional area is LW, and then delta T over H. And then the same thing will flow horizontally along that blade, namely Q triple prime, H, L, W, and then conductivity of the path, the cross-section of the blade that's expensive, that cross-section is D, W, and then delta T, X over L. When I'm canceling this W, I'm reassuring myself that my analysis, even though written for 3 dimensions, is in fact valid for a 2-dimensional looking object. It is, we're searching for the drawing of the object in profile. All right? Well, okay, without, beating this little problem to death, we have expressions for the 2 temperature differences. We pull them out of here, we substitute them here, and then we get the following expression, which is that the total, in fact, yeah, that's right. This expression becomes a Q, the total Q, L over Kp. By the way, I wrote them in the wrong order. I'll put them correctly. QH over K0. By the way, the conductivity here was K0 according to my drawing. This K0. All right, so LW. And then the other one is QL over Kp dW. And And then we divide this expression, this one, divided by the constant factor, which is Q divided by K0 and W. So we get that the total delta T divided by Q and then K0 and W equals, in an order of magnitude sense, forget about equal, it is equal to two terms, H over L plus K0 over Kp, and then in here we multiply and divide by H in order to get d over H is 1 over phi, according to meaning H over D is 1 over phi, and the K0 over Kp is 1 over K tilde, where K tilde is, I write it here, is the ratio of the two conductivities which is much bigger than 1. In other words, the object of the game is H over L plus this factor 1 over phi K tilde, and then L over H. So all this, in order to reproduce the centuries-long battle between Roman 1 and Roman 2. This is Roman 1 and Roman 2. And the so-called victory or stalemate occurs when these two terms are of the same order of magnitude. In this case, if I set them equal to each other, it means I've reached the sum that's the minimal sum. So from 1 the same as 2, I discover the shape, which turns out to have the expression H over L, and I write it optimal in an order of magnitude sense, equal to 1 over square root of what I wrote here, K tilde, and then phi. So that's the answer when it comes to architecture. What is interesting about this answer is that whereas K tilde is bigger than 1 and phi is less than 1, the product, well, you don't know what it is. It could be of order 1, meaning that the drawing, in other words, you arrive at a family of drawings, most of them flirting with what I drew, meaning a drawing that's easy to make. And obviously, if it's meaning making an easy drawing is the introduction to manufacturing something easily, you see. And one more thing, if you substitute this discovery in the formula for basically the overall heat transfer resistance, you obtain, and then K0W divided by Q. That turns out to be of order K tilde and phi to power 1/2. This is the best you could do, you see. And both factors, K tilde and phi, every single one of them costs money. You want no, it's the other way around. Yeah, it's upside down. I wrote it upside down. Minus 1, 2. Minus 1, 2. So to have a lower thermal resistance, you have to invest into an even better conductor and buy more of it, a greater phi. The reason I bring you to this punchline is to remind you that we do, in this case, science, because we're being egotistical. We want to live more easily, which means longer, farther, all of that per unit of wallet volume. So that's money. This is money. Get it? Or, by the way, there are two problems in heat transfer. One is, in this case, cooling, is to make the object cold when the heat current or the heating is fixed. But if you imagine the upside down of this, which is this business K tilde phi, if the temperature difference is fixed, that means, yeah, the temperature difference is fixed. I think this is more like the problem of the cooling of electronics. Temperature difference is fixed because you want this object, your laptop, not to melt its electronics. So this is fixed. Q, you want more and more of it, which means to pack more and more circuitry at work inside your box. Get it? So to minimize that means to, so that's to minimize, means to maximize this. And both problems are both exclamations are about the same discovery, which is the discovery of the architecture that, as I said, in thermodynamics is not forget about mention, is not on the brain of those thinkers. Thermodynamics is about black boxes, and that's a great thing because thermodynamics applies to anything that you wish to imagine putting and morphing inside that box. All right? On that note, make sure you show up on Wednesday. That means that you're rooting for my own ability to show up, okay?